We're group 4 and we completed the 3D reactors lab. In this experiment, we used SolidWorks to design 3D reactors which varied in total reactor volume and reactor geometry. These reactors were 3D printed and used to test how varying reactor geometry and reagent flow rates affected conversion of an alkali bleaching reaction. We hypothesized that increasing reactor volume and decreasing flow rates would increase residence time and thus increase conversion. This reaction happens when malachite green reacts with sodium hydroxide. Malachite green has a deep blue color in solution, but loses this pigmentation after reacting. A spectrophotometer was used to measure the transmissivity of light through the solution exiting the reactor, which could ultimately be used to calculate conversions. As previously stated, all reactors were initially designed in SolidWorks. These 3 reactors varied in total volume and potential flow pattern.
The 3 reactors we designed were the T reactor in the SolidWorks tutorial, a snake reactor, and a circular channel reactor. The T reactor had a simple geometry where both reactants met in the middle and formed the product. The snake reactor also has a simple geometry, but with a much greater volume and residence time when compared to the T reactor. The circular channel reactor has a complex geometry as well as the greatest volume and residence time of the 3 reactors, and is expected to yield the highest conversion of malachite green. At the start of each day of testing, a new calibration curve was made by creating a series of dilutions from the stock malachite green solution and then graphing the transmittance values observed by the spectrophotometer. This allows for the outlet conversion of the malachite green from each of the reactors to be measured by comparing the experimental values to the values on the calibration curve to determine the final concentration of the reactant.
In our experiment, we first had to find our calibration curve. This takes multiple concentrations of malachite green solutions and calculates the transmittance of malachite green coming in. Since it knows our transmittance going out, it can make a rough estimate of the malachite green concentration in our reactor and outlet stream. In our experiment, we took 10 milliliters of malachite green in each trial and ran it through each reactor with multiple flow rates, that being 1, 2, and 5 milliliters per minute. Each flow rate was ran through twice in each reactor. These flow rates entered through one inlet stream, with sodium hydroxide being the other. When both streams enter the reactor, a reaction was formed.
In order to compare our experimental results to the theory, we uploaded our SolidWorks reactor designs into COMSOL Multiphysics. This software allowed us to predict mixing and conversion in each reactor by specifying flow rates and reaction information. Here are tabulated results for all trials, including residence time, which was calculated using inlet flow rates and reactor volumes, predicted conversion values from the COMSOL simulation, our experimental conversions derived from average PC ratings and the calibration curve data, and a value called the Pecklet number, which is a dimensionless number that compares convective mass transport to diffusive mass transport, informing us about the mixing behavior in different reactors and/or flow rates. Here, averaged conversion values from each trial are plotted against their corresponding residence time. T-reactor data disagrees with our hypothesis, as conversion decreases with increasing residence time. However, this is likely due to faulty calibration curve data. The serpentine and spherical reactors behaved as expected, with increasing conversion at increasing residence times. Also, the spherical reactor has significantly greater conversion values, as expected. However, data is not significantly statistically differentiable, so we do not feel confident confirming our hypothesis. Here, experimental conversions for each reactor and flow rate are plotted against those predicted by the COMSOL simulation. With the exception of T-reactor data, general trends between the 2 datasets agree, as increased volume and decreased flow rate result in greater conversions. However, experimental values seem to be consistently greater than those predicted. The dotted line represents what would be perfect cohesion between predicted and experimental values. This disparity is likely due to the previously mentioned faulty calibration curve data. If we better calibrated the spectrophotometer, we would predict more agreement between these values. In conclusion, our hypothesis was neither confirmed nor denied. Experimental data indicated trends in agreement with our hypothesis. However, these trends couldn't be confirmed by statistical analysis. We expected the circular channel reactor would have the highest conversions because of its increased volume and complex flow pattern. The data agreed with this. In order to confirm our hypothesis, we would ideally perform more calibration curve testing to better calibrate the spectrophotometer. We would also devise a way to make sure the spectrophotometer was exposed to the same external conditions every trial, so outside light could not affect the readings. We would also perform more trials for each reactor to ultimately find statistically significant differences between varying flow rates and reactors. This has been Group 4's 3D reactor video article. Thanks for watching.